For 5,000 years or more, man has built cities. And when man builds cities, and he builds all the buildings in the city, man also builds gaps between the buildings, roads, so that people can walk and travel and carry goods. And for 5,000 years or more, there were only roads. But then, in the 20th century, a new invention appeared. A new machine. And for a time, it didn't matter. Man still built roads, same as he always did. But he started to put a little concrete platform on the side of the road for people to walk, so that they could be safe from the machines. Many years later, now human beings don't even venture onto the roads. They just stay to the sidewalks, except to cross. The real invention was not the car. The real invention was safety. In yesterday's video, I discussed how we might represent the city, the traffic network, buildings, pedestrians, cars, planes, and all the other things. And I did some thinking last night, and here's how I want to deconstruct the world. So we have agents, which are people, cars, buses, planes, animals, robots, ghosts and goblins, anything that moves around. We have segments. I think I'm going to change the name of this. I don't know if segments is really what I want. The segments are roads, buildings, and could represent a lot of different things. And agents move within segments. So they're in a segment and they move around within the segment. We have parking spaces, we'll get to that. We have connectors. And connectors connect segments. So you can think of a doorway, or you can think of the threshold between an intersection and a road. Tenancies are places that you want to be. So it could be your home, it could be a business, it could be a shop that you want to go to, it could be school, it could be a public park. And decorations are just there for visual appeal to make the city look nice. And we'll come back to parking spaces in a second. So roads are segments. So you have a segment of a road. That's where the name comes from. And your house is a segment. So the structure of the building is a segment, and you can be inside the house. In the demo that we've been working on, there's a little path, or the guy walks, along a path, but I don't actually render the path. And there's also a driveway which the car drives on. And the driveway will have a parking space. Maybe it could have 2 parking spaces, I don't know. And it has a car, which is an agent, parked inside of it. So the person comes down from the house, gets into the car drives onto the road. Now there's connectors connecting the driveway and the house. The car drives down the road, and then I'll put them all on this side because there isn't enough space here. Then the mall has a driveway and a parking lot, and then the mall itself. There's some connectors like doorways here, 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 and connecting the driveway for the parking lot for the mall to the road. And there's some parking spaces inside the mall. Computer will, of course, make them all a consistent size. And then the mall inside of it has some tenancies. Which would be businesses. So these would be shops that you would go to. Your house also has a tenancy inside of it, which represents that you live in the house. Let's finish the path. So you go down the driveway into the parking lot, and then you go in here and you park here. Or the character does. And then the character walks internal to this segment. So all of these agents essentially can freely move within the segment, and there'll be a routing algorithm that will really only look at the connectors. So it'll go from this connector to this connector to this connector, here, and then maybe it has some knowledge of parking spaces, so it finds the parking space. Or maybe that's done automatically by the car. And then you go into the mall, and maybe you go into a tenancy, I don't know. Or you have some sort of temporary relationship with the tenancy for, you make a purchase. So basically roads and buildings are the same thing. That's what this comes down to. And cars and people are the same thing. They're both agents. But I might, make a distinction between the representation of the agent traveling around and the representation of, the person, and the person, has maybe like social relationships, and they have a home, and they have a place of work, and so on. And that, so this structure might evolve over time. So the way that this game works is, there's some person wants to go somewhere, and so there's a routing algorithm that runs in the background and finds a path and finds a destination, and then the person stores the path, or the vehicle stores the path, and the vehicle travels along that route, and then the vehicle has like a physics simulation internal to the segments. How's this going to work? Let's talk about an intersection, or really just the roadway leading up to an intersection. Actually, let's use a new layer. Because there's a bit of a problem that I have that I'm trying to sort out. So, as I said in my little dramatic intro, for 10,000 years or however long we've been building cities, I know that there's been some debate about that lately on the internet, but I don't care what the date is. For many millennia, we've been building roads as just kind of regions of space. And by the way, these segments do not have to be square. They don't. They can be any arbitrary polygon, including, like a computed curve polygon, like that. So a curved road would look like this. It would be maybe a higher resolution, and the computer can make the lines all straight and nice and curved looking. So here's a segment that represents a curved road, and it might have connections here, maybe here. Maybe it has two connections to its intersections, and then it also has connections to some driveways that are connecting it to some buildings. And the router determines, what does the router determine? The router just cares about, okay, we're going from here to here, or maybe the router wants us to go all the way to here. Now you notice that because this is a concave polygon, yes, a concave polygon, the vehicle would want to take a path that goes off the road. So, one strategy could be that we could break up segments that are curved like this into, smaller segments that are guaranteed to be convex. I better get this right. I always remember that a concave has a cave in it. Get the jargon correct here. So we could divide curved roads into many smaller segments, but I don't really want to do that. So my thinking is that if the router gets the wrong length here, maybe that's okay. And there might be a bit of a limit to how curved roads can be. Maybe if you do like a circular road, that you have to break that up into segments the same way that you have to break up a circle on an expressway into smaller segments. Or the game manages that for you, maybe. But for kind of a softly curving road that just has a little bit of this concavity, maybe we can just ignore it for the purposes of the router, and then when the agent, the car, moves through the segment, it has to know that it, can't go into the walls here. And what I want to do is, this is more of a long-term thing, is that there's going to be a quantum simulation. So when you're not looking at the road, it only does kind of the blue part of the simulation. Then when you do look at the road, the game generates the more visually appealing simulation where the cars flow around each other. It generates that simulation on the fly. And how it'll work is if you have a road that has a lot of cars in it, it'll use the information about how far along the blue path the car has gotten. So the blue path is like the coarse-grained simulation, and the green path is the fine-grained, visually appealing simulation. And when you look at the road, the game has to generate the fine-grained, visually appealing simulation. So what it'll do is, if it's high density, it'll just kind of pack the cars in according to some packing algorithm. And I'm going to start with how traffic flows in most of the world and in most times in history, where traffic was just kind of free flowing. It was kind of just like a fluid, and it will only do that simulation when you're looking at it. When you're not looking at it, it just tracks how far along the path has the car gotten, and how many cars are in the segment, meaning like how much traffic is there, how much congestion is there. If there's a lot of congestion, then everything will just flow slower, but there won't be any collision detection in the coarse-grained simulation. In the fine-grained simulation, there will be collision detection or collision avoidance, and these cars will all kind of route around each other and try to make their way through the segment and stay within the polygonal walls and so on. So let's take a look at what I drew yesterday. We have pedestrians and cars, and a bunch of other things, but I just want to focus on the pedestrians and the cars. We have sidewalks here, and we have a crosswalk. And then we have another sidewalk here. And that creates a bit of a puzzle, because we can represent this in a bunch of different ways. We could represent it as just one big segment, and the people and cars move around within the segment. And that works pretty well for this kind of, how people don't drive in rich modern countries. How people used to drive and how people drive in other places. Which is something that I want to simulate. But for, the structured driving, so, the term I'm trying to avoid using is third world, because I don't care for that term. But what I'm getting at is that different places have different levels of traffic discipline. So this is the term that I'm going to use, is traffic discipline. So in some places, people just go all over the place, and in other places, like say Germany, for example, so I'm told, people really do follow all the lane markings and never go out of the lane, and pedestrians never jaywalk. I don't know if that's true about Germany. Maybe that's true about Japan. It's somewhat true about the United States, to a certain extent. People do jaywalk a lot in the United States, but there's a lot of traffic discipline in some countries. And particularly sidewalks create a bit of a puzzle. Because one way we could do it is we could simulate a sidewalk and then a crosswalk, and then the actual road, and then a crosswalk on the other side, and then the other sidewalk on the other side. And then we'd have connectors going between. Connector here, connector here, connector here, connector here. And then where do the cars go? So the cars have to connect too. So they go through the crosswalk, because we don't really want these segments to overlap, because we want to do the collision avoidance. So this is a lot of graph work. And in the old game, we also divided the road into two, because there were two directions. So you're going one way or the other way. And then how do the crosswalks work? Or there's a lot of structure going on here. And the more segments we have, the slower routing is, the more difficult routing is, it puts constraints on how big the city can be. And let's see, I drew out here, this is what an inner city might look like, according to this model. So you have roads, connectors, we have crosswalks. So let me just show you how everything would flow through, starting with pedestrians. So let's say you got some guy coming off the metro, and the train itself has kind of like a parking space here in the station. And the guy's in the train, and then he gets off the train, and then there's this underground tunnel. So this part is underneath the city. And there might be like a little shop here. And then he goes up the staircase, and he could go here and he could wait for the bus. And these little yellow squares are kind of like seats. You can think of it as a parking space for a human. And this red square might represent the bus stop. This yellow square represents where the bus stays to do the bus stop. He could also go here, he could go across the crosswalk, he could go around here, he could go into a shop, maybe the buildings connect. We have parking spaces for cars here. These light blue squares are tenancies, so those are businesses. Maybe there's a newspaper stand next to the metro station. But so last night I was thinking about, okay, well, we got to have all these different segments for the roads going different ways, and how do we do crosswalks? But I think what I might do is I'll start with this. I'll start with the low traffic discipline case where, people are just kind of unstructured flowing through the space. And later on, I can implement, I'll reuse the blue color, but I don't see these as connectors. But maybe I'll put, kind of like a structure here, so like at this end of the road, there are crosswalks and pedestrians can pass. And on this side of the road and this side of the road, there are sidewalks and pedestrians can pass. And within the crosswalks, the pedestrians can collide with the cars. But I think that it's going to be kind of like general collision detection. So, the people walking around, they might walk around here. And then if there's a car coming here, they might kind of virtually react even though they're on the sidewalk. So they might appear to go, further into the sidewalk so that they're not too close to the car. But their algorithm will tell them to stay within the kind of area bounded by the blue lines. So they, you can go across the crosswalk, and then he'll really be paying attention for the cars. and then he can go to the other side. So this concept of traffic discipline and sidewalks, traffic discipline would be the cars, stay on the correct side of the road, meaning the right side in most countries. The and they might also have some knowledge of the lanes. And let's see. If we have like a curved road like this one, how do we represent this substructure within the road? You've got sidewalks on the side. I guess the cars also have to know about the sidewalks, because when the cars are moving around, they're not supposed to go onto the sidewalk. So I might have to generate the substructure. I think that this is going to be an issue for a future date. So we're going to table this. We're going to do the low traffic discipline case. Where did everything go? Okay. So we're just going to do this kind of low traffic discipline case where everybody is free flowing. My paint program broke. There we go. The text tool for this program, Krita, is annoying to use. It's really annoying. And on this side, we have high traffic discipline. You guys get the picture. So, we did a lot of whiteboarding, and I wanted to do some programming. So I set up, let me go show you guys some of the code here. I set up new agents. I set up a table for agents, three tables actually, within this database that I'm working on. And I wasn't going to call the database cursor, but the cursor is the object that you interact with the most. So I worry that might end up becoming the name of the database. So this cursor database has, it's like a tree structure, so you can get this table agent position, and then you can use it as an iterator, so you begin, and then in the for loop you say, is it a value, go to the next value, and you can read the mesh index, the position, and there's also a target value, which is not used for drawing. So this part here relates to the drawing of the agents. And the agents are just these cars and buses that are moving back and forth, not following the road path, because right now it's just a very simple algorithm. They just march along a line between where they start and their target. So let's go look at the update function. So now I've separated updating the agents into a separate task from the draw task. Now in the draw task, I still have, here's the draw task, I still have this scripted code that I wrote in yesterday's episode. And in the scripted code, the car looks at this spline, evaluates spline tangent, and we could make the vehicles, these new agents, follow the spline. Or we could start to implement this kind of collision detection that I was talking about. So the collision detection would look at the shape of the road, the polygon that makes up the road, as well as the locations of other agents in the segment. And it would try to find a path that avoids both the walls and the other agents. Let's see. And, it might actually become kind of a routing algorithm. But for right now, let's just focus on a, kind of an old-fashioned algorithm that would be like an old-fashioned game AI. Just looking at the walls and where it wants to go and the positions of the other agents. And we'll start with the walls and we'll get to the other agents. But let me go over more about how it works now. So here's the update function. I get two cursors here. I get a position cursor and a target cursor. And the position cursor I'm using as an iterator. So I say begin here. Then I'm iterating over the position cursor, using it as an iterator. And the cursor points to an array, basically. And it has to be an array, in fact, because that's how we get the best performance. So this is I'm trying to implement something that's called structure of arrays. And the way that most programming is done is array of structures. So you have an array, and every element of the array is the complete information on that particular object, whether it's a car or a road or a person. And so every time you want to look at the car, you have to look at everything about the car. Its color, what year it was made, where it's going. You have to store all of that information in the same place. And maybe you don't want to know all that information, and it's kind of a performance issue, is that the CPU has to load a bunch of information that isn't relevant. So we're dividing up our information into these tables. So there's a position table, there's a target table, and there's a mesh table. So we start with the T object, we say at agent position, and then we begin to use it as an iterator. For the target table, we start with the T object, we say at as vec3, and then the table name, which is agent target. We name these tables up here. We just say name and then the name of the table. And when you use these tables, you have to know what type you're using. So here we're using a vec3 for the mesh table. So there's mesh table, position table, target table. For the mesh table, we're using it with U32s. That's just something the programmer has to remember. And this is going to be a very difficult interface for people to program on. And I'm doing it this way because I'm interested in performance and getting the best performance possible. And I know that that's a little farcical because I'm getting FPS on 420 agents, 40, 50. Part of that is OBS, but part of that is that there's, much more optimizations to be run. It might be because I was getting 165 before, so and I changed the size that it's rendering, so it's doing super sampling, trying to get some anti-aliasing. And this is, all this stuff can be optimized, but I'm planning ahead with this database, this very terse, difficult to use, confusing database, because I'm hoping that I'm going to get the performance that I want out of it. And if I don't get the performance that I want, then I'll ditch it and I'll try something else. This has become my obsession over the last, few years. So, okay. So let me put some comments on this code. Update all the agents. Reset the animation. So if I comment this code out, then every time the animation loops, all the other cars will disappear. And it'll restart. Now down here, we're adding new agents. And what we do is we say, is the agent count less than the camera time? I wonder if when it loops, I guess it's probably going to generate like a few dozen agents all at once. Like, oh, there you go. That's probably generated like, several dozen agents at one time. That's funny because I don't reset the cam time value, and I'm not sure if I can. So let's not reset the animation. So now the agents won't reset, which wasn't working anyways. So they'll just build up, and we can, if we let this run for a little while, we can see, if there's 1,000 agents, if there's 10,000 agents, does that cause the game to slow down? And, while we're watching the animation, we can think about how to make this algorithm. You can see here we have almost 1,000 agents. We're still not really losing anything in terms of FPS. Now, this is obviously not ideal FPS. I'm tempted to ask AI about this. I'm either going to ask AI or I'm going to go back to whiteboarding because I'm actually not sure how I have to think about this. So supposing that we're this car. Oh. Well, my computer's lagging, so maybe there's something awful going on in the background. It doesn't look that bad. Okay. Well, we've got some agent, and where are they going? Their target is over here, let's say. Maybe there's a driveway over here that they're trying to get to. Now the agent can go directly to the target, but there's this guy in the way. So it has to know that it's supposed to go around this way. It's almost like a routing algorithm. I know that there are routing algorithms in 2D, like basically for this case, but I don't think that we really want to do like a very sophisticated routing algorithm. I think we just want the idea that like you kind of go around barriers. So it's kind of like, if you're here and you're trying to get over here and you see this wall here, you have to like tangentialize your vector. Like you have to make your vector tangent to this barrier. I think I am going to ask AI. Well, ChatGPT is not that smart. So let's see if Claude 3 is a little smarter about it. This Claude 3.5 is really a lot smarter than ChatGPT. Okay. I'm going to go take some code from an old friend. If I remember where I put it. Point, line distance. Yes. We probably want line distance 2D. Line distance. Oh, looks like we don't optimize for 2D. Oh, this is such a complicated algorithm. I'm glad that I didn't try to re-implement it. So we'll just yank %. And we'll put it in. Right. 0, vec3, 1, vec3, b0, vec3, b1. Line distance. Tag include collision .h. I want to put, oops, in the wrong file here. I want to put this, using a terminal as an IDE is a bad idea and you shouldn't do it. Okay, we have to have camera.h for GLM. And actually that's all we need. And then when we used it in the code, line intersection. So 32 dist equals line distance. Next post, P1, P2. Okay, and then if dist is less than, yeah, sure. Okay, cool. So Claude is finding a collision between the car and the polygon of the line. If there's a collision, that's interesting. So it reflects the vector around the collision normal. Okay. First, let's get my code to compile before we start integrating Claude's code. Templates in C++ suck. Okay, so I've taken the code from Claude. Let's see, we need a clamp function. I bet if I just put the word namespace somewhere, I wouldn't have to type GLM over and over again. Well, I've done something funny. Corrupted double linked list. You know, programming in C++ is the highest form of masochism. It's really awful. I don't know why I do it. Okay. Right here, invalid right of size 8. And we get it in load polygon. So let's see what we did wrong. Wait, this is in spline, it looks like. Line 74 here. So we're probably writing past the end of what we've prepared here. Although I'm surprised that that would cause this kind of issue. Because when I write to this location... Oh, I'm probably not checking to make sure that I don't go below 0. Although I don't know why we would go below 0. Let's do a little printf debugging, see what we're doing wrong here. Wait, how do I get rid of this now? Good lord. There we go. This looks good to me. So I'm doing this in kind of a funny way. I'm loading the polygon for the shape of the road into the database. And here I'm writing backwards. I don't know if that's the issue. If we just don't do this writing here. Okay. Don't use U32s, fam. U32s are terrible. Well, there's some weirdness there, but oh, wow! That actually kind of works. So it looks like they are able to get onto the other side of the wall. I didn't expect this to work. I'm asking AI to do something very complicated here, and it did it. These computers are getting too smart. This is not a good thing, fam. It's interesting. There's a bunch of different error conditions here. They can get stuck on the wrong side of the wall. Looks like they bunch up at the end. They're not able to get to their endpoint. Now, I don't know if I actually got the shape of the polygon correct, because, you know, we're having trouble with this function here, and we're doing something kind of sophisticated, so we really should find some way of testing and verifying that we got a polygon at least somewhat sensible. But look at that. The cars actually kind of flow. I mean, I know that they glitch out and they get on the wrong side of the wall. Essentially, there's like a wall, and they won't go on the, you know, they're not supposed to cross the wall, but once they do cross the wall by mistake, they're kind of stuck there because they're still not supposed to cross the wall. So that's interesting. But hey, I mean, like, this actually looks pretty good. Let me get one little detail before kind of investigating where this glitch is coming from. Let me just get the rotation, because I think that'll look pretty nice if we have the rotation correct here. So I'm just going to add a new table, agent rotation. And we're going to use it as an F32. And AI is just going to figure this all out for us. Do we use this word travel somewhere else? Oh, vtravel. Okay, so we're writing the rotation of every agent into our database, and then we're going to go down to drawing. Here we draw the agents. This 0, we're going to read this from the database, equals C agent wrote. There we go. What? I broke something there. What did I do? Wow, I really broke something here. What did I do? What did I get wrong here? Okay. So I'm still doing something wrong when we're loading the polygon. On line 76. Now this is the problem, is now I can't get rid of this darn thing. Doing this leak checking. Well, why didn't we get the printf here? I put a printf here. I'm gonna figure out a way to debug this stuff without having to kill the program. So this is why C++ is perceived as hard and why it is hard. 0 bytes after a block of size 0 alloced. Let's take a look here. So why is it preparing something of size 0? Oh, I think I'm maybe using this incorrectly. No, this is how this is how I was intending to use it. If it doesn't have the index, it prepares the index, meaning that it makes sure that that index can appear in that array. Let's go back and look at our leak check. So this leak check.sh that I'm running is actually a Valgrind. And Valgrind is a program on Linux, and I think you can get it on Windows too, that well, there's really supposed to be a printf here. Because it gets to line 78 here, So why doesn't it hit these printfs? Or we're just not seeing them? Very strange. So when you're programming in C++, you get some very strange outcomes because the computer does not protect you against anything. So you can get some very strange behavior. We're preparing it. 0 blocks after a block of size 0. So, okay. I think that we should never alloc a block of size 0. Now this is probably going to crash all over the place. I'm putting an assertion saying, let's not allow ourselves to ever alloc a block of size 0, because that just seems wrong, like something wrong has happened. Is 0 bytes after a block of size 0? Well, why is this even being allowed? Why is this occurring? Maybe this is wrong. Maybe Valgrind is not figuring out the size of the block and it's just saying that it's a block of size 0. Because clearly it would trip this assertion if that happened. According to Valgrind, we actually did get to line... Oh! Hold on. Okay. So maybe it didn't get there. Maybe do I have insertions enabled? I thought maybe I disabled assertions because I wanted to see if there was an effect on the performance. Okay, so do I have... You know, this is very confusing. Am I in debug? Is this being compiled as debug? I have no idea. I think if I put this here, now I'm going to have to recompile everything. And there's probably going to be a bunch of assertions that gets tripped. You know, these days compiling a big C program actually doesn't take as long as it used to. It's gotten a lot faster now that compilers are multi-threaded. There we go. So we're calling, when we call prepare, we have to have the unit size here. Okay. That was a big unnecessary journey, but I'm sure was very confusing to everyone. Now let's go back to what we were trying to do, before we got sidetracked on fixing this awful database. We're trying to make these agents rotate. Here we want this to be rot. Okay. And I'm betting, we have kind of some weird glitch behaviors, and I'm betting that we set the collision avoidance too high. So we have let's see, we got a hitbox radius here, and let's just set this to 1, and maybe it'll look a little bit nicer. Well, that's interesting. Let's try 2. Well, I noticed in the other places we subtract a factor of 90 degrees. Well, this is going to be funny. I think that we're going to maybe debug some of these glitches in tomorrow's episode. I might call it a day here. Has some weird fun behavior, doesn't it? It's very strange. And I forgot about parking spaces. So, yeah, parking spaces are parking spaces.